Hello and welcome to part 2 of this problem. In the last video, we went over the entire algorithm for how we're going to solve this problem, these coplanar forces, and finding the resultant of all the coplanar forces. In this video, we are going to write Python code to solve this problem. We're going to write a script to solve this problem. So if you have not watched the last video, I would highly recommend it because I go over this entire algorithm, some edge cases, some things with the direction, all of that sort of stuff, and it explains the problem more in depth. But in this video, we are going to write Python code to solve this problem. So again, very briefly, the problem statement states that given a bunch of coplanar forces, find the resultant force acting at the central point of those forces. So we're going to assume that all of these forces are going to be acting on this single point right here. And these forces can be positive or negative, but they are going to have directions given by the theta angles, this diagram. Okay, so to start off, remember the first step was to create two lists of our input. One is our forces and one is our angle. So if we go back to our IDE here, what I'm going to do is I'm going to start off by saying, well, I'm going to declare a variable called forces, and I'm going to create a list of different forces. Now, I'm just going to put down any random numbers of forces, just like that, and we'll say that these forces are in newtons. So these are newtons. Now I need a second list for the angles, and these angles are going to be in degrees. So that's very important. Angles are in degrees. Each one of these angles correspond to the direction of the corresponding force. So this element right here, this is force, we could say F1, the first force, that has a magnitude of 32.2 newtons. And the direction that that force makes is this right here. It's 45 degrees from the positive x-axis. And so another example here is this 12.3 Newton force. The angle that it makes with the x-axis is 180 degrees. Now, all of these values that I'm inputting here, they are float values. They are not integer values. They are going to be float values. Awesome. So if you remember back from our algorithm, that was kind of step one. So we've figured out step one here. We need input for forces and angles. Secondly, we wanted to check to ensure that the lists are equal in length. Now, if they are not equal in length, we just need to exit the program and tell the user that, hey, go ahead and check your input forces and your input angles and try again. So what I can do here is I can say if length of forces does not equal the length of angles, then I want to print to the console some error message saying that your input is correct. So I could just say your input is incorrect. Please check it and try again. And at this point, I just want to exit the script. So in Python, we can exit the script by saying quit. So if the condition for this if statement is true, then we're going to get a message in the console and we're going to quit the program. Now we can actually try this. We can go here and say, okay, well, what if I just took away this negative 7.9? So now the list of forces is only 4 elements, but the angles are 5. So if I run this, we should see this error message in the console. And of course we do. Your input is incorrect. Please check it and try again. So I'm going to go ahead and add that force back in because we need it. And now if we try to run this script, we should just not see anything. So I forgot to clear it here, but let's try it again. If I hit play, you can see that nothing is printed out, which means this condition right here, this length of forces does not equal length of angles. That was false, so this block never ran. Okay, awesome. So what was the next step? Well, if we go back to our algorithm, step 3 was to in order to find the resultant force, we need to find the components of the resultant force. Now, remember, I said when we write our script, we need to iterate through all of these forces, find each force's x component and y component, and add that to some running sum of the x direction and the y direction. And so I need to create two variables here to track that running sum as we iterate through each one of these forces. And here I just called it x sum and y sum, so we can call it something similar in the script here. I can say x component sum is equal to a float of 0, and y component sum is also equal to a float of 0. So we're just initializing two variables to keep track of our x component sum and our y component sum, and we're going to use this later to find the resultant magnitude. Okay, so what was after that? Well, we need to break each force into its x and y components. We need to keep a running sum of all the x and y components, and then we can determine the resultant vector using just Pythagorean theorem here. So in order to do that, we need to iterate or loop over each one of these forces and angles. And so I kind of have pseudocode written here for each force and angle. I want to take x sum, whatever it was, and I want to add to it the corresponding force times the cosine of the angle, and the same thing for the y component, right? Y sum is going to be equal to the previous value of y sum plus the force times the sine of the angle. So if you're confused with this plus equals thing, let's go over that in code. So what I'm saying here is, well, first we need that for loop. So in Python, I can do something like this. I can do for force index and force in enumerate forces. We need to pass in the list of forces. Then I can do something here. So this for loop right here, it has an index and a force component. And enumerate just means that we can track the index for each of the elements that we're looping over in forces. Now, each element I'm just going to call force for each iteration of the loop. And this for loop is going to give me the index of this force. So the index of this first force is 0. The index of the second element, the second force is 1, and then so on, 2, 3, 4, etc. Now what I can do here is say x component sum is equal to x component sum plus the force times the cosine of that angle. Now, if we try to run this, we are actually going to have a problem. Let's try to run this. Name cosine is not defined. Well, that's because cosine is actually a method in the math library. So up here, we need to import this thing called math as m. And m is just a shorthand notation for math. You can name this whatever you want. I just named it m for simplicity. So what I can do here is I can come back down here and I can say m dot cosine of that angle. Now I actually made another mistake. I just called this angle. Where is this angle coming from? Well, remember, for each force, there's a corresponding angle. And so this index value here is going to give us the index that we can use to retrieve the corresponding angle for the force that we're looking at for the current iteration of this for loop. So I can say, I can create a variable here called angle, and that is going to be angles of the index. So if index is 0, that means we are iterating over this 32.2 force, and when we run angles bracket index, it's going to give us 45. And on the next iteration of the loop, we're going to have an index of 1, and that's going to give us 62.4 because we're on force 85.6. Okay, awesome. So let's go over this line, line 15 right here. I said x component sum is equal to x component sum plus force times the cosine of the angle. Now, you might be confused here. Why is there x component sum on both sides? Well, remember, this equal sign here isn't actually an equal sign. It's the assignment operator. And what the assignment operator does is it evaluates the expression on the right side of it, and then it assigns that value to the left side variable here. So what this line is doing is it's taking the x component sum, which is initially 0, right? Up here it's 0. It's adding to it the x component of the force here, and then it's reassigning x component sum to be that value. And so for every iteration of this for loop, we're going to have an incrementing or maybe decrementing if the x component is negative for that particular loop. And at the end of this for loop, so after it's iterated through every single one of the forces, our x component sum variable here is going to have some value. Now, we also need to do that for the y component. So y component sum is equal to y component sum plus force times m dot sine of angle, right? In order to find the y component of a force, we need to use the sine function. Now, there's actually a way to make this code a little bit more concise. If you remember I had something like this written in our algorithm. So I had this thing, this plus equals. And what plus equals is it's just a shorthand version of this y, x component sum equals x component sum plus this force times cosine of angle. This is just a shorthand version of saying, hey, we need to take this variable, we want to use that in our calculation here, and then we want to reassign x component sum for this line of code. And I can do the same thing here. Instead of saying y component sum is equal to y component sum plus some other value, in this case force times the sine of angle, I can just shorthand this to plus equals. And it's going to do the same thing as the line we just had. Okay, so we've done quite a bit of work already. This for loop is pretty extensive. It's doing some really powerful stuff. It's calculating the sum of all of the x components and all of the y components of this force list that we have up here. So to make sure that we are doing things relatively correctly, let's go ahead and print and just check what these x component sums and these y component sum variables are, just to make sure that all of these calculations are working correctly and that we don't have any syntax mistakes. So I'm going to print here, firstly, I'm going to print the x component sum. So I'll say I'll say the x component is x component sum, and then I'll also print the y component. So the y component sum is y component sum. Now, if you're not familiar with this syntax, there's this f here right before the string that we create. And this f just means we're going to print an f string. And what an f string is that we can take different variables and we can plug them into the string that we want to print. And so what this is going to print is x component is, and it's going to take the value of this x component sum that gets calculated in this for loop and plug it in there, and then do the same thing for y component. So let's go ahead and run it with these inputs here. And we should see what the x component sum of the resultant vector is and what the y component sum of the resultant vector is. So let's hit run, and you can see that the x component is 150 and the y component is -5. Now, I want to bring your attention back to where we're calculating x component sum and y component sum, because these values that we're getting in the console are actually incorrect. Now, if you remember, I said that the angles that we're dealing with are going to be in degrees. But this cosine and this sine function from the math library is expecting a value in radians. And so when we're passing in this angle value, what we're passing in is a degree version of that value. So what we need to do here is we need to take this degree angle and we need to convert it to a radian angle. And the way that we can do that is we can again access the math library and say m.radians and then pass in the angle. So what this is going to do is it's going to take the angle in degrees, convert it into radians, and then pass that value to the cosine function. And we can do the same thing here, m.radians of angle. So now when we go and run this, I'm going to clear this first and then run it, you'll see that our x component is 82 and our y component is 34. So that is looking pretty good. Okay, so what was the next part in our algorithm? Well, once we figured out the x sum and the y sum, what we need to do is we need to determine the magnitude of the resultant force. And that's pretty simple to do. We're just taking a squared plus b squared is equal to c squared, and we're solving for c. In our case, our resultant magnitude is c. So let's go ahead and do that in code. I'm going to delete these print statements because we don't need them anymore. Now I'm going to create a variable called resultant magnitude. And that is going to be the square root of x component sum squared plus y component sum squared added together. And then you take the square root, right? Just Pythagorean theorem. And that's going to be m dot square root. And again, we're accessing square root from the math library. Square root of x component sum squared plus y component sum squared. And so the way that we write square is with these two asterisks. So x component star star 2 is x component squared plus y component squared, and then you take the square root of that and you get the resultant magnitude. Awesome. So now if you remember from this print statement exercise that we did, you'll notice that we have a lot of decimal points. We don't really need all those decimal points. We can make them, up to only 1 decimal point or 2. I like using 4 in a lot of my calculations, so that's what we'll do here. What I'm going to do here is I'm going to say that the resultant magnitude is going to be equal to this round function, and I'm going to pass in resultant magnitude, and I'm going to say 4. Now let me explain what this is doing. What I'm doing here, again, this is not an equal sign. This is a assignment operator. So it's taking the value on the right side and reassigning it to this variable here. What this round function is doing, the first argument we pass in is the value that we want to round. And the second argument is the number of decimal points that we want. So in this case, we want to pass in resultant magnitude from this calculation on line 18, and we want to round that down to 4 decimal places. And once this round function executes and runs, it's going to assign that value to resultant magnitude. In this case, it's just going to reassign resultant magnitude to this value. So we can make sure that this is working. We can say print fprint or fstring, right? The resultant is resultant magnitude. And I should really, instead of saying resultant, I should say the magnitude of the resultant force is resultant magnitude. Now, if we run this, I'm going to clear the console, and I'm going to run. It says the magnitude of the resultant force is 89.0283. Now that looks a lot nicer than 89.02834667 blah blah blah, whatever the other numbers are. We just want to round this to 4 decimal places. So I think that looks good, and we can move on to the next step. Okay, so what was the next step? I'll go ahead and delete this print statement here. And now we have the resultant magnitude, right, based off of this calculation. Now the next step was that we need to determine that resultant force's direction, or the angle from the horizontal x-axis. And if you remember from the last video, we can't simply use the tan inverse of y over x. We have to use this method a tan 2 and pass in the y component and the x component of that vector, of the resultant vector. And this a tan 2 method will take care of figuring out which quadrant that resultant vector is in. Because again, regular arctan is only going to give us an angle value in the first and the fourth quadrant. It's not going to consider the second and the third quadrants. And we had some edge cases to worry about, right? If the x component is 0, you'll see here that that's going to be undefined, right? You can't take some number and divide it by 0. So we also have to take care of these edge cases. And if all of those edge cases are not met, then we can simply calculate the angle using a tan 2 of the y component and the x component. So let's go ahead and do that. The very first thing I'm going to do is I'm going to create another variable called resultant direction. And I'm going to initialize this to a float value of 0. Now, this is also going to be in degrees. We have to make sure that this is in degrees because we're trying to keep units consistent. So now, some of those edge cases that we were talking about, I can say if the x component sum is equal to 0 and the y component sum is equal to 0, then I want to do something. I want to say that the resultant direction is just going to be 0. So that takes care of our first edge case here. If x sum is 0 and y sum is 0, then just say that theta is equal to 0 because there really is no resultant force, right? If the x components and the y components are 0, then the resultant is 0. And so we can just default to theta equals 0. And so that's what I'm doing here. Resultant direction is equal to 0. Now let's move on to the second. Else, if x component sum is equal to 0 and y component sum is positive, then I want to do something else. Well, what was that something else? I said that if the sum of the y components is positive and the x components are 0, then we know that the resultant force is just acting straight up. So we can say that theta is equal to 90 degrees. And that's what I'll do here. Resultant direction is equal to 90 degrees. Now, third case, else if x component sum is equal to 0.0 and y component sum in this case is negative, then I can say that the resultant direction in this case is negative 90. Now, if none of those conditions are met, then I can say that the resultant vector is going to be the calculation of a tan 2. So I can say that resultant direction is equal to math of a tan 2, and this method, again, takes two arguments. The first is the y component, and the second one is the x component. Now, be very careful. This returns radians, but remember, we want our resultant direction in degrees. So the way that we can do that is we can let a tan 2 calculate what the angle is going to be in degrees, or I'm sorry, in radians, and then do our conversion ourselves. So resultant direction is going to be m dot degrees of resultant direction. And so what this is doing is first we're calculating resultant direction here on line 30. This value is going to be in degrees, and so we pass that value right here into the degrees function, and it's going to convert this radian value to degrees and then reassign that value to resultant direction. And so this resultant direction is in degrees. Okay, cool. So after this, we basically have our resultant direction and we have our resultant magnitude. And now what I can do is I can print the resultant magnitude and the direction to the console, and we should have our script. So here I'll say that the resultant is equal to resultant magnitude, and then maybe I can just do a new line here, and I can say direction, the direction of the resultant force, is going to be resultant direction. Now, I'm going to go ahead and run this, and we'll see what's printed out into the console here on the right. And there we go. We have a resultant of 89 units of force, and the direction is 22.9 degrees from the x-axis. Awesome, so we solved our very first statics problem in Python. However, I do want to go over some more edge cases because there's actually one other thing that I didn't tell you that we didn't go over, and I want to show you that there is a slight problem in this script. Now, if you know Python very, very well, you might see what the problem is, but if you don't worry. It's actually very, very complicated unless you go through a lot of different edge cases. So the edge case that I want to introduce you to is, firstly, I'm going to comment out forces and I'm going to comment out angles, and I'm going to recreate those here. And I'll say that in this case, we're going to have two forces, and that's going to be 1 and 1. And the angles is going to be 0 degrees and 180 degrees. So if you can kind of imagine, the first force is going to act exactly to the right at 0 degrees, and it's going to have a magnitude of 1. And the second force is also going to have a magnitude of 1, but it's going to act in the exact opposite, so exactly to the left. So this is acting to the right, this is acting to the left. You know intuitively that the x components are going to cancel out, and there is going to be no y component. And so if we run the script now, you should think that the resultant force is going to be 0, and the resultant angle is going to also be 0 because, well, we said that if x component sum is 0 and y component sum is 0, then our resultant direction is going to be 0. Well, let's make sure that is still the case, so I'm going to run it here, and we have a problem. The resultant force is correct. However, the direction is saying 90 degrees. That doesn't make any sense. We said that if the x component sums to 0 and the y component sum to 0, then we want the resultant direction to be 0. However, it looks like this second else if statement is running, and it's saying that the resultant direction is equal to 90 degrees. Now, why is that? Well, to figure that out, we need to peek into these x component sum and the y component sum variables and see what they are. Because for some reason, it's thinking that the y component sum is positive, which means it's greater than 0, and it's running this case when it really should be running this case. So let's go ahead and do that. Let's print the y component, or the x component and the y component. The x component sum is just x component sum. And I'll print another statement here, and this will say y component sum is y component sum. So let's save this and run it, and let's see what happens. Let me actually clear this and retry that. So, okay, this is interesting. It's saying that the x component sum is 0, but the y component sum is 1.2246 times 10 to the negative 16th. That is interesting. It isn't saying that the y component sum is 0, even though it truly is. If you have one going to the right and one going to the left, then you know the y component is 0. But here it's saying it's this super, 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 super tiny number. And the reason this is happening is because computers are really, really good at storing very, very accurate values. However, there might be some rounding issues when we're computing all of these different variables, the x component sum, the y component sum, the magnitudes, the directions, all of that stuff, especially when you start putting them into other functions. For an example, if you put them into the Pythagorean theorem, you're squaring x component sum and you're squaring y component sum. And so any inaccuracy you had in the original x component sum or the y component sum or both just get magnified when they're squared, right? So somewhere here, our decimals are very, very, very slightly wrong. Now, obviously not a problem to human calculations when you do it on pen and paper, but when you plug them into a computer, it can get very dangerous. So what we need to do here is, instead of just simply plugging in x component sum and y component sum with, I don't know how many decimal points of accuracy that these functions are calculating and assigning to x component and y component, what we need to do here is we need to round x component sum and y component sum to something reasonable so that when they are passed into other functions, that any inaccuracies don't get magnified. So after this for loop, this is what I'm going to do. I'm going to say that x component sum, we're going to round x component sum to just 4 decimal places. And y component sum, we're going to round that to y component sum, to 4 decimal places. So now that we do that, this x component sum and this y component sum, they're only going to have an accuracy of 4 decimal places. So when we pass in those values here, we aren't also including these tiny, tiny, tiny little discrepancies in the calculations that get carried over in some of these calculations. Okay. So, a lot of gibberish, but basically we're just rounding down numbers to reasonable accuracy and then using that in our calculation. So now when we go and do that and we hit play, you'll see that x component sum gets rounded down to 4 as a maximum decimal places, as well as y component. And when we do that, our resultant is 0 and our direction is 0. So awesome. I think this is working and it's looking good. Congratulations on your first statics algorithm using Python.